Hello everyone. In this video, we are going to discuss practice exercise 2.2 from second chapter of Elements of Electromagnetics. So in this numerical, we have to convert the given vectors into its Cartesian coordinate system. So if you look out for your very first one, so this vector is expressed in terms of rho, z and phi, which is basically expressed in terms of the cylindrical form. So this is the cylindrical form of your given vector, and we have to convert it into the Cartesian one. And if you look out for the part B of the same numerical, so it is expressed in terms of r, theta and phi, which is basically is what? It is expressed in terms of the spherical form. Okay, so whatever these two vectors, we have to convert these two vectors into its Cartesian form. So for that purpose, we are going to make use of the some uh, conversion expressions that I will express over here. And for this video only, we are going to discuss part A of the same numerical and part B that we are going to discuss in the next video. Okay, so we will start with what is given to us. So we are given with vector A, which is basically expressed in terms of cylindrical form, and we are going to assign some equation to this one. So for this, I'm going to say this to be equation 1 for your reference purpose. Then next, if you look out, so what is this given vector A? If we are going to write it in the forms of elements and components in its cylindrical form, then we can rewrite this equation to be what? That is A rho cap, then this a phi cap, and this will be what now? Az cap. Okay, so this is the generalized form of any vector which is expressed in terms of cylindrical form. This is the generalized form. Now if you are going to compare equation 1 and 2, so before comparing that one, let me write some conversion expressions that we are going to use. So if you have seen my earlier videos, so we have that conversion expressions. So if we are given with some Cartesian system or Cartesian coordinates, and if we want to convert that Cartesian coordinates to cylindrical form, so what sort of expressions that we have used earlier? So in order to convert any of the Cartesian system into a cylindrical form, we are going to make use of this equation where we have that rho, which is equals to square root of x square plus y square. So this gives the value of that rho. Then next is we have the phi, and that phi is what? That phi is nothing but tan inverse of y by x, and z. So z is as it is. Okay, so if you have that values of x, y and this z, so by using that one we can convert that any of the Cartesian system into cylindrical form. And next is vice versa of this one. So if we are given with the value of that cylindrical coordinates, cylindrical to Cartesian one, that means if we are given with the value of that rho, phi and z, so we can make use of this expression where we are going to convert that rho, phi and z into x, y and z. So for that x, we have that value to be what? X is rho cos of phi, then y is rho sin phi, and this z is as it is. Okay, fine. Now if you look out for the second expressions, that is the conversion of that cylindrical to Cartesian one. So what value we have for that x? So x is equals to what? X is equals to rho cos of phi. Now from this we can rewrite your cos phi value. So what will be that cos phi value if you look at over here? So it can be rewritten as whatever is your x, sorry, whatever is that cos phi. So that cos phi will be what now? This cos phi. So what is left? This row will be over here. So that will be what? X is nothing, cos phi is nothing but what? X upon rho. In similar fashion, we can write the value for that sin phi. So what is that sin phi? So sin phi will be y upon rho, and this z, so that z will be as it is. Now again we can make use of this value of that rho. So what rho value we have? That rho is equals to square root of x square plus y square. So from this again we can rewrite that cos of phi is nothing but what? So this cos phi will be x upon value of that rho, and that rho is equals to what? Square root of x square plus y square. So this will be your cos phi, and sin phi will be what now? So sin phi will be again y upon rho, and that rho is equals to what? Square root of x square plus y square. Okay, so you just write these equations for your reference purpose somewhere, since we are going to make use of these values for simplifying this numerical. Okay, so this is the very first part. Now in the next part we are going to compare these equation 1 and 2. Okay, so we have equation 1 and we have equation 2. So we are going to compare these equation 1 and 2 to get the value of that a rho, a phi and a z. So comparing equation 1 and 2 we get. So what values we are going to get? That a rho, whereas this capital A rho indicates what? Component of that rho along rho direction. Okay, so if you are going to compare this a rho and this a rho cap with respect to this one, so what is the value of that a rho we are going to find? So that a rho is nothing but what? Rho z sin phi. So a rho will be what now? Rho z sin phi, and you can refer the previous slide for having the values of that rho z and sin phi. So if you are going to look out for this one, so rho is what? Square root of x square plus y square, or else left that one, simply you just put the value of that sin phi. So what is that sin phi value? From this previous slide we have that sin phi is equals to y upon rho. So we are going to place that value, that rho will be as it is, that z will be as it is, and from this slide what value we have for that sin phi? That sin phi is equals to this one. Sin phi is what? Y upon rho. So place that value over here for your reference. I am going to put that one. So that rho z is equals to y, sorry, sin phi is what? Y upon rho. So what is left? This row and this row, it will get cancelled out. So we are left with the value of that a rho, which is equals to what? Y and z. Okay. So for your reference, I am going to assign this to be as equation A. Now in similar fashion, we can go with the value. We are going to compare that a phi from equation 2 with a phi from equation 1. So what value we are going to find for that a phi? So that a phi will be this one. So a phi, for now we will have that to be the 3 times rho cos of phi. So we are going to keep that 3 as it is, this rho as it is, and from the previous slide, so what value we get for that cos phi? So that cos phi is equals to x upon rho over here. Okay, so that cos phi is equals to what now? X upon rho, and this here in this case, this row and this row, it will get cancelled out. So what is left for the value of that a phi? So we have that a phi is equals to 3x only. So assign some equation to this one. Say for now this is to be b. Again for that az, so az will be as it is because we don't have any change over there. So this is az, and from this we have the value of that az, which is equals to what now? Rho cos phi sin phi, and if you observe for your upper two values, so that cos phi is what? Just we have written that cos phi is nothing but x upon rho, and this sin phi, so this sin phi is nothing but what? Y upon rho. Okay, so here in this case, this row and this row, it will get cancelled out. So what is left? we are left with that Az is equals to xy upon rho. But this is again we have the value for that rho. If you see for this previous slide, so what is that rho? So we are going to make use of this value over here, that we have that rho is equals to square root of x square plus y square. So place that value of rho here in this case. So we have that Az is equals to x y upon rho, and that rho is nothing but what? Square root of x square plus y square. Okay, say for this to be equation C. Now, if you are going to make use of that equation A, B, and C, and if you are going to put that all three values in your say equation 2, so we are going to get the value of that vector A, which is partial in terms of Cartesian system and partially in terms of that cylindrical system. Okay, so uh, okay, so I will write it for you. So using A, B, and C, you can say whatever using or putting that values in equation. Say for now, equation 2. Okay, so using equation A, B, and C in equation number 2. So we are going to rewrite your vector A, which so that vector A is equals to what now? A row. A row, what value we have found from this A? So A row is nothing but what? YZ A row cap plus this A5. This A5. So A5 value, what we have? That A5 is equals to 3x. So that will be 3x into this A5, and then this AZ. So AZ, we have that value to be what? XY upon square root of x square plus y square AZ. And this is what? Again, assign some equation. So I guess you can say this to be equation 3, isn't it? Yes, equation 3. Okay. So if you observe your equation 3, so what values we have for that components along that arrow A5 and AZ direction? So these are that components, which is YZ. This is X over here, and this is again in terms of that X and Y. So that's why I have said it is partially Cartesian system and partially cylindrical system, since we have that unit vectors along that rho phi and z direction, so which represents as cylindrical form of that vector. So we have that partial vector which is expressed in terms of Cartesian as well as cylindrical system. Now we are going to fully convert it into the cylindrical system as they are stated in part A of the numerical. Okay, so for this purpose we are going to make use of some reference table that we have seen earlier. So we have to express this equation 3 in terms of cylindrical, we have to express this equation 3 in terms of its Cartesian coordinate system. This is what. Okay, sorry. So we are going to make use of some conversion table that we have seen earlier. But before that, whatever this vector A in terms of that Cartesian system, it will be expressed like this one. That vector A will be what? Ax cap plus ay cap plus az cap. Okay, so I am going to assign this to be equation 4. Now for your reference purpose, I am going to put that conversion table so that it will be quite easier to you. Now if you are going to compare equation 3 and 4, so okay, so let's write it again over here. So we are going to compare equation 3 and 4 in order to get the value of that values of ax, ay, and az. So from this we get that ax. So what is that ax? Ax will be your given vector A having the dot product with respect to ax. Okay. Now what is that given vector A? So that given vector A is nothing but your equation 3. So we are going to rewrite that one, your equation 3 again over here. So that will be yz a rho cap plus 3x a phi cap plus xy divided by square root of x square plus y square az cap. So this is what is your equation 3, and it will have the dot product with x. Okay, sorry for this bracket over here. Now we are going to make use of this dot product table to have that conversion. So start having the dot product with respect to each and every vectors, unit vectors over there. Okay, so this yz will be as it is for now. The dot product in between that a row and ax. So dot product in between this a row over here and this ax over here. So that will be what now? The dot product in between a row and ax is what? Cos phi. Okay, fine. Then this plus 3x will be as it is. Now we have the dot product in between this a phi and this ax. So dot product in between that ax. Okay, so this ax and this a phi. So that will be what now? Minus of sine phi. So that is minus of sine phi. 3x is as it is, sine phi, and the dot product in between that az and ax. So the dot product in between, let me rub it for you. Dot product in between that az and x. So that is what? This is ax and this az over here. So we have that value to be 0. So okay, fine. So we are going to write this to be the 0. Okay, fine. So we have the value of that ax, and what is that ax? So ultimately we are going to get the value of that ax to be yz cos phi minus 3x sin phi. Again, if you see what values we have over here, we have that cos phi and sin phi. So if you are going to refer the previous slide, so we are going to put the value of that cos phi as well as sin phi. So cos phi is what we have, x upon square root of x square plus y square, and that sin phi, what value we have for that sin phi, that is y upon square root of x square plus y square. So we are going to put that values in this equation over here. So again rewrite that one. We have that ax is equals to yz cos phi. So cos phi is what? X upon square root of x square plus y square, then minus 3x sin phi. So what is that value of sin phi? That is what? Y upon square root of x square plus y square. Okay, so this is what we have the value for that ax, and again assign some equation to this one. Before that, if you want, you can rewrite that one, since we have that in the form of that yzx. So we can also say it to be what? Xyz. So say it to be xyz so that it will look nicer. So that will be what now? xyz upon square root of x square plus y square minus 3xy divided by square root of x square plus y square. And for now we are going to say this to be the equation number 5. Okay, now we are going to find out the value of that ay and az in the similar manner. So in the previous part we have found what is the value of that ax. Now here in this part we are going to find out what is the value of that ay. Okay, so again we have equation 3 and equation 4, and if you are going to compare that equation 3 and equation 4, from that we can get the value of that ay. So what is that ay? We have that ay will be nothing but your given vector a having the dot product with respect to the unit vector along y direction, that is ay. So your vector a is what? Which is given to be yz arrow plus 3x a5 plus xy upon square root of x square plus y square, and this is az, which is having the dot product with respect to ay. Again, make use of this transformation table as we have used earlier in order to get the dot product in between these two values. So we have that yz as it is for now, the dot product in between that arrow and ay. So what is the dot product in between that arrow and ay? So this is what we have, that arrow. So arrow having the dot product, dot product in between that arrow. So this is arrow having the dot product with respect to ay. So which is what? Sine phi. So we have that value to be sine of phi plus this 3x will be as it is. Now next is the dot product in between this a phi and this ay. So the dot product in between that a phi and ay. So this is what we have, that a phi, and this is your ay. So dot product in between that ay and a phi is nothing but what? Cos of phi. So write that cos phi over here. Then the dot product in between that az and ay. So we have that dot product in between that this az and ay, which is to be what? 0. Since that value is 0, so I am not going to write it again. That value which is 0. So we are left with that ay is equals to what now? Yz sine phi plus 3x cos phi. Now you can make use of this earlier slide where we have that sine phi to be what? Sine phi is what? Y upon square root of x square plus y square, and where that cos phi is what? X upon square root of x square plus y square. So put that values over here. So from this we will get that ay. So this yz is as it is sine phi. So sine phi we have that to be y upon square root of x square plus y square. Okay, then next this 3x, so this 3x will be as it is, and what is that cos phi value? So we have that cos phi is equals to what? X upon square root of x square plus y square. Okay, so from this we have that ay, which is equals to yz into y. So that will be what now? That will be y square z divided by square root of x square plus y square plus this 3x into x. So that will be what now? 3x square divided by square root of x square plus y square. So say this to be equation, I guess earlier we have assigned that equation 5, isn't it? Okay, yes. So this ay we are going to assign it to be equation number 6. Okay, now next part we are going to find out what is that value for that az. So your az will be what now? Sorry, I have written it earlier. Now again we are going to compare equation 3 and equation 4 in order to get the value of that az. So that az will be what now? Your given vector a having the dot product with respect to unit vector along z direction. So your given vector a is what? We have that value to be yz arrow cap plus 3x a phi cap plus xy upon square root of x square plus y square az cap having the dot product with respect to az. Okay, now again make use of this dot operator table in order to have the dot product in between these two. So I guess you have come to know how to take the dot product. So that's why I'm going to directly rewrite that one. So write this yz as it is for now. So dot product in between that arrow and az. So dot product in between this arrow and az is what? So 0. So this will, the very first term will be what now? 0. Dot product in between that a phi and az. So dot product in between this a phi and az is equals to 0 again. So again put that value 0 over here. Now the dot product in between that az and az. So dot product in between the two same vectors is what now? This az and this az, that is equals to 1. So we are left with that value, which is xy divided by square root of x square plus y square. So this is the value for what? So this is the value for that az. Okay. So again assign some equation to that one. I guess we have assigned that equation 5 and 6. So say for this to be equation number 7. Okay, so this is what is your equation 7. Now in order to get that values of that equation 3, so this is what equation 3, which was partially in terms of Cartesian system and partially in cylindrical system. So we are going to put the values of that equation this 5 over here for that ax value, then equation 6 for that ay value, and equation 7 for that az value. So again I'm going to rewrite it for you. Okay, so sorry, we are going to put, so putting equations, or you can say whatever, that 5, 6 and 7 in equation 3 and rewriting. We get, okay, so we will get that vector A is equals to what now? Vector A is equals to x, y, z divided by square root of x square plus y square, then minus 3xy divided by square root of x square plus y square, ax cap plus, within second bracket we have y square z divided by square root of x square plus y square plus 3x square divided by square root of x square plus y square, which is ay over here, and then again plus xy, which is your equation 6, sorry, equation 7, xy divided by square root of x square plus y square. This is az cap. Okay, so we have that vector A, which is completely expressed in terms of x, y, z, which is what it is. We have expressed that vector A in terms of that Cartesian system. And again, for simplification, or in order to look it nice, so we are going to separate out that square root of x square plus y square besides that one. So take that 1 divided by square root of x square plus y square common from all of the brackets, because it is everywhere over there, and within this square bracket we are going to say what is left, x y z minus 3xy ax cap plus y square z plus 3x square ay plus xy az cap. Okay, so this is how we have expressed that vector A in terms of its Cartesian coordinate system. In the next part, we are going to talk about the part B, where we are going to convert that spherical coordinate system into its Cartesian or rectangular form. Okay, so this is what is our answer. If you appreciate my efforts, you can hit the like button and share it among your friends to subscribe my channels. Okay, thanks for watching my video. Thank you.